What's up, everybody, and welcome back to OpenStax Algebra and Trigonometry, Chapter 6, Section 8, Fitting Exponential Models to Data. Let's do it. So the first question is, what situations are best modeled by a logistic equation? Give an example and state a case for why the example is a good fit. So a logistic function is really good for something that maybe at some point might be growing exponentially, but then it is going to level off, right? And the idea about leveling off is that there's a max capacity. So a great example would be a virus spreading through a population, okay? So it might be that the cases might at some point rise exponentially. First we have 2 people infected, then 4, then 8, then 16, just as an example. But that growth, that rate of growth doubling, it's not gonna continue, it's not sustainable because at some point, you're going to start getting to that point where you're going to, let's say, infect more than half of the population. Then now the rates, they can't keep rising. They're going to slow down. They're going to level off. And the max infection rate is the total population of whatever the city is or world is or whatnot. So that's the idea. We are going to use a logistic model when we have a cap point, a max point. So there you go. Boom, done. So this one says, what is regression analysis? So the idea of regression analysis is you're going to take existing data points from a scatter plot, right? Let's say you have a few different points like this, and then you're trying to fit a model to it. So would this set of data be best represented by a linear equation? Would it be best represented by some sort of exponential model, or maybe logistic even as it levels off? So the idea of regression analysis is taking these points and seeing what type of mathematical model would fit best with these data points. And the idea is you're trying to pick one that's going to accurately predict the future. So if you pick linear and then the next point is like over here, okay, that's maybe not a good model. But if you pick logistic and it models it this way, and then the next point's over here, right? When you plot it out, that makes sense. That's a good predictor. So that's how you perform regression analysis. Obviously, you're going to use the help of a calculator, and hopefully that will help you pick the appropriate model. But that's the idea. Done. What does the y-intercept on the graph of a logistic equation correspond to for a population modeled by that equation? So it's kind of like the y-intercept in general. It's always our initial value. So if we're talking about population, it would be the population at quote unquote times 0, whenever that might be. So bottom line is it's the initial population, boom, done. So for numbers 6 through 10, we're going to kind of do them together by looking at all the graphs and all the functions simultaneously. So let's first look at number 6. It's an exponential function, e to some negative coefficient times x. Otherwise, that would be a nice typical graph that would look like this, that would go up. But because it's negative, that's a reflection across the y-axis. So we're looking at something like this. So number 6 is either going to be C or E, right? These have those correct shapes. But we're going to have to differentiate between the two. And I see there's a pretty big difference at the 2 value, right? Here, 2 is 6. Here, 2 is 4. So let's plug and chug 2 in for x. And when I plug it in, I'm actually getting 5.67. So that's sure looking like E. So on that basis, I'm going to go with E for number 6. So now we come to number 7. And this one is interesting because it's a logarithmic function, which usually looks like this. But because there's a negative in front of it, again, it's flipped. This is a flip over the x-axis, which means it's now going to look like this. This would be a vertical shift up by 5, but it's again the same shape like this and like this. So again, it's got to be C or E, but since we've already eliminated E, this one has to be C. Now we come to number 8. This is a nice typical exponential growth. You see that this value is greater than 1, and then it's to some exponent. We have a constant here that's going to give us a nice y-intercept of 2.104. So it should be a typical model going up like this. The only one that really looks like that is A, so I'm pretty sure that 8 is A. Now we come to these two. This is a typical logarithmic function with a vertical shift up by that much, but it should still kind of look like this. And then we've got this one, which is a nice logistic function. So I'm looking at this logistic function, and again, this top value is the upper bound, which is a little over 14. So if I'm now comparing between the remaining graphs of B and D, okay, for the logistic, D sure looks like the logistic. D sure looks like number 10. It looks like it's capping off at about 14. So on that basis, we're going to go with 10 being D, that nice logistic function, and then number 9 being the remaining one, which is B up here. So that's how you answer these problems. Boom, done. For this logistic function, we're asked two questions. We're asking what is the initial value, that is when t equals 0, and then we're asked what is the carrying capacity, which you can identify just from looking at the equation, but we'll come to that second. So first, the initial population, we plug in 0 for time. That becomes e to the 0th power, which is 1. So it ends up being 175 over 1 plus 1 times 6.995, which is just 6.995, like so. And in a calculator, this equals, rounded to the nearest whole number, about 22. So that is the initial population. And then the carrying capacity is this top number, that numerator. So the carrying capacity is 175. So that's how you do it. Done. For number 13, it says a logarithmic model is given by this equation. It says to the nearest hundredth, for what value of p does h of p, does the function equal 62? So let's plug and chug and we'll solve. So we have this equation and now we're meant to solve for p. So we're going to isolate first by subtracting 67.682 from both sides. Next, we're going to have to divide by this coefficient of negative 5.792. And this gives us a value of approximately 0.981. That's rounded, okay, equals that ln of p. Now, last but not least, we're going to convert this to its exponential equivalent form since it's ln that's base e. So it's e to the 0.981 equals that argument of the logarithm, which is p. And when you evaluate this in a calculator, you get p equals approximately to the nearest hundredth, 2.67. That's your answer. So for 15, they're asking for the y-intercept of this model up here. And again, that's the initial value, aka the value of the function when t is equal to 0. So we're going to plug and chug. And then 0 times negative 0.42 is 0. E to the 0 power is 1. 1 times 5 is 5. So 1 plus 5 is 6. So it's 90 divided by 6, which we can do mentally to be 15. So the y-intercept, therefore, in coordinate form is 0, 15. Boom, done. For number 17, we're using this equation, and we're asked to find the initial population, which is the function value when x is 0. So let's plug and chug. Okay, 0 times negative 0.28 is 0. E to the 0th power is 1. So we get 68 over 1 plus 16 times 1, which is 16. So that's 68 over 17, and you can do that mentally, and that's 4. So the initial population of koi was 4 koi. Boom. For this one, it says, how many months will it take before there are 20 koi in the pond? And this is the equation that was given. So when we're saying when there are 20 koi, again, the function value represents the number of koi. So we're going to plug 20 in for p of x. And since x is the number of months, we're going to solve for x. So first, I'm going to multiply both sides by this denominator. And when I multiply the right side, it just cancels the denominator. And then the left, it goes like that. And now we have to distribute. So I get 20 plus 320 e to the negative 0.28x equals 68. Then we're going to subtract both sides by 20. And that gives me 320 e to the negative 0.28x equals 68 minus 20, which is 48. Last but not least, divide both sides by 320, like so. And we get e to the negative 0.28x equals, and that simplifies to 0.15. And I shouldn't have said last but not least. There's still one more step, or actually two more, because now we have to bring this exponent down. It's locked in an exponent, the variable I mean, and to bring it down, we have to use logarithms. And since I have e, it's really convenient to use natural log, okay? So I'm gonna take natural log of both sides, and that allows me to first bring the exponent down as a power, negative 0.28x times ln of e. But the beauty of ln of e is it's 1, so it just goes away, equals ln of 0.15. Last but not least, we're going to divide both sides by negative 0.28, and we get ln of 0.15 over negative 0.28. So you plug it into Desmos, and you get 6.775, which rounds to 6.8 to the nearest tenth, which means it will take approximately 6.8 months. Boom, done. So for this one, it says graph the population model to show the population over a span of 10 years. And I'm going to use Desmos to do that. So let's check it out. To see the population over a 10-year span, here's time 0 with that initial population of 10.145 and kind of going up literally to 10 right here. So at 10 years, it's roughly 364. And just to point out, you see that numerator, how that's the carrying capacity, 558. You see it levels up pretty much at 558 eventually as we go beyond 10 years. But just saying, so that's what the graph looks like. Boom, done. So this one says, how many wolves will the habitat have after 3 years? So this is a plug and chug situation. You just plug 3 in for x and solve for p. And to do that, I'm going to use a calculator. So let's check it out. So here's the function. I'm going to replace x with 3, and we're going to evaluate it. So here's the function, and all I did was replace x with 3. And here I get 38.47, which would round down to 38. And you can also see on the graph that when I look at 3 years, there it is, right? It's right there at that 38.472, exactly what we calculated. So we can say approximately 38 wolves is the answer. Boom. This says use the intersect feature to approximate the number of years it will take before the population of the habitat reaches half its carrying capacity. So we're going to go back to the function on the graph, and I'm going to show you how to do this. So first of all, what is the carrying capacity? It's 558. It's that numerator. So half of that would be 279. So we're going to set y equal to 279. That's going to make a nice horizontal line. And we want to know when this intersects our function, and it intersects it right here. That's the beauty of Desmos. It's just there. You click on it, and this would take about 8.6 years because that's the units that it's in. So we would say approximately 8.6 years. Boom, done. So for number 27, it says use the regression feature to find an exponential function that best fits the data in the table. So to do that, we're going to use Desmos. So check it out. So here we've plotted all the data 1, 2, 3, 4, 5, 6 with the corresponding y values. And then we've run it through this regression for the exponential, and it gives us the following constants. So let's plug and chug. So now as we enter this, it's the function equals, and then for that leading term A, it's 776.682. And then the B value is 1.426. And all of this to the x power. That's how you do it. Boom, done. So for number 29, it says graph the exponential function here that we got in number 27 on the scatter diagram of the values from the table. So we're going to plot that now in Desmos. So here's the exponential function in blue that models these data points. And if you look, it looks really good. It looks like a really good approximation. It's really hitting most of those points. So that's how the two look together. That's how you do it in Desmos. Done. So for 31, it says use a graphing calculator to create a scatter diagram of the data. So we're going to use Desmos to do that. So here's a little plot with the points. So there's your scatter plot with those 6 points. That's how you do it. So when you plug this data in and first create an exponential equation through the regression function on the TI-84, you're going to get this. So now we need to convert this to a base of e. So what we can do is we can say we need 0.738 to the x equal to e to some exponential power. So let's call this t, for example, and we need to know what t is, right? So what we're going to do is we're going to take the natural log of both sides. We get ln of 0.738 to the x. Again, using the natural logarithm or any logarithm powers, we can bring that exponent down here. So I can make that x ln 0.738, equals ln of e to the t, which again allows me to bring the t down. Now this is great because ln of e is just 1. So now I know that t equals x times ln of 0.738. Since e to the t basically replaces this, which is right here, I can now rewrite it as f of x equals 731.92, and then we're going to go e to the t power, but t is this. It's x ln of 0.738. So what is ln of 0.738? Let's calculate it. So it approximates to negative 0.3038. So then just replacing that, we get our final function, which is equal to 731.92 e to the negative 0.3038 times x. And that's how you do it. Boom, done. So using the function that we found in 33, we're going to use the intersect feature to figure out when this equals a function value of 250, and we're going to do it in Desmos. So let's check it out. So we got the function graphed here, and we're trying to figure out when this hits a function value, aka a y value of 250. And boom, there it is. Now we can use that nice intersect feature, but in Desmos it's pretty easy. We just literally click the intersection, and it's occurring when x equals 3.536. So that rounds to x equaling approximately 3.5. Boom, done. So here it says to use a regression feature to find this logarithmic function from this data set. And what I'm going to use is I'm actually going to use Desmos because this is going to give us a really good answer, same as what we have in the back of the book. So let's check it out. So here's the logarithmic regression. I just plugged and chugged those points in as follows, and we get the following values for A and B in this format, which is going to be perfect. So let's write it out. So we get y equals, and I know it says A here is the constant, here it's B. So I'm just going to put that first 5.06, and then we'll round up to the nearest 1,003, and then plus what would in our case be the A value, right, times the logarithm, times the natural log. So that's 1.93, and then that rounds up to 4 ln of x. So that's how you do it. Boom, done. So for number 39, we're meant to graph the logarithmic equation that we got in 37 from the regression analysis to these data points. So let's check it out in Desmos. So again, here in red is the regression for this exponential or logarithmic, excuse me. And then here are the points, these little black points here. So that's how it looks. It looks like a pretty good model because it's hitting or really going kind of through the middle of all these points. So that's what it looks like. Done. So for this one, it says use a graphing calculator to create a scatter diagram of the data. So let's do that now in Desmos. And here are the points plotted. This is what it looks like, and that's it. Boom, done. So for this one, we're meant to find a logarithmic function that models the data from the table, and then we're meant to find the value when x equals 10. So using the logarithmic regression model in Desmos, we're going to just flip that on here with the points already entered from the table. And then we get this nice model here, right? And you can see that it looks pretty good. And then we're trying to find the value when x equals 10. So we're going to move it over just a touch, and we're going to set x equal to 10. It's going to make this nice vertical line, and we look at the intersection point, and it looks like it intersects when the function value is 2.322. So rounding up to the nearest tenth, we'll say roughly 2.3, boom, done. So for this one, once again, we're going to use the regression model to figure out what value of x is going to make the function value equal to 8. So we're going to use Desmos, and from the last problem, we already have the logarithmic function pulled up here using this nice logarithmic regression in Desmos, and now we want to figure out when the function value is 8. So we're going to set the y value equal to 8 and look for that x value at this intersection point, which is approximately 0.818. So rounding up to the nearest tenth, it'd be roughly 8.2, boom, done. So for number 47, we got to plot all these values, and then we got to run a logistic regression to get a nice equation. And by the way, we got 7, 8, 9, 10. So we're going to plug these points into Desmos, run the regression, and let's see what we get for the constants. So here we plugged everything in as x1 and y1. Here's our model for a logistic, and here are all the values. So let's plug them in and let's see what we get. So we get y equals, and then that first value on top, in our case it's a, it's 25.08, and then rounded to the nearest thousandth is 1, divided by 1 plus, in our case it's b, which is 3.182, times e to the negative c, which is 0.545, times the variable x in this case. So there's the logistic function model for this data. Done. So for this question, it's asking for the predicted carrying capacity of the model to the nearest whole number. And I put back the regression logistic function that we got in the previous exercise so you can see. And we use Desmos, by the way, to calculate that. So the carrying capacity is this numerator, and this rounded to the nearest whole number is 25. So that's the answer. Done. So for this one, we're meant to use a graphing calculator to plot these data points in a scatter plot or scatter diagram. So let's do that now in Desmos. So now that we put in all the points like so, we can see here is the scatter plot. This is what it looks like, and that's it. Done. So 53 is asking to graph the logistic equation of the data points on the scatter diagram. But what we're going to have to do, because this was question 52, we have to run the regression analysis and get that graph, then we can plot it. So I'm going to do all of that in Desmos. So in Desmos, it's great. Once we have the points in, we just kind of run this, right? This is how we create our regression model for a logistic function in this format. So we're just going to turn this on, and boom, there it is. These are the constants. And this is what the graph looks like. And you see how nice that is? It goes right through those points pretty accurately. So that's what the graph looks like. Done. So here we're going to use the intersect feature on the graph to find the value for x when we reach half the carrying capacity. So first we're going to have to look at the model again. And since the numerator here is 136.068, that's the carrying capacity. So what's half of 136.068? Well, I'll just write it in like this. And then we want to know when the function reaches that half point. So we're going to say y equal to that value. And then we're going to look at the intersection point on the graph, which is occurring right here. And there's our approximate value for x, 4.866. So this will round up to roughly 4.9. That's the answer. Boom, done. So this says to use a graphing utility to find an exponential regression for f of x and a logarithmic regression for g of x for the points 1.5, 1.5, and 8.5, 8.5. Okay, so in Desmos, what I did is I put in those 2 points, 1.5, 1.5, 8.5, 8.5, and then this is the exponential regression that I've run in Desmos, where they're finding values for a and b, and this is in purple. And then in red, we've done our logarithmic function, which is a plus b times the natural log of x sub 1, and these are the constants that is found there. So now we can kind of see what they look like, and then to graph it with y equals x, that's what we're putting in blue here, okay? you can see that it kind of looks like these guys are symmetric about the line y equals x. So what does that say? When two functions are symmetric around the line y equals x, that implies that they're inverses. And these functions are pretty darn close to perfect inverses of each other. So that's how you do it. Boom, done. So this says to find the inverse of this function. So we're going to start with our typical process. We're going to change the f of x to y. Then I'm going to swap the x and the y. And then we're going to isolate y. So first I'm going to multiply both sides by this denominator. So of course, when we multiply the right side, it just cancels out. And the left side, it multiplies by the x. And now we could distribute, or we can just simply divide both sides by x because we're trying to isolate that y. So let's just divide by x. And then we get 1 plus a e to the negative by equals c over x. Next, I'm going to subtract 1. So let's do that up here. Okay, and now we're going to get rid of that a. So let's divide both sides by a. This equals c over ax minus 1 over a. Now we need to get this variable y out of the exponent. And to do that, we need to use logarithms. And since I have a base of e, the best choice is natural log. So I'm going to take natural log of both sides. And that allows me to bring the exponent down as a coefficient, negative by. And ln of natural log of e is 1. So it's literally negative by times 1, which equals natural log of this whole thing. Now my last step is to divide by negative b, and we get ln of c over ax minus 1 over a over negative b. So this is slightly different than the answers in the back of the book, so I'm going to show you how we go from this to that answer in the back of the book, but I just want to let you know this should be an acceptable answer. But what they've done basically, they factored out 1 over a times c over x. Now it's just minus 1, right? So I factored that 1 over a out. And I still have negative b down here. Now, using my logarithmic properties, I can break this up. Since these two arguments are multiplying each other, I can break it up into a natural log of 1 over a plus natural log of c over x minus 1. And then ln of 1 over a is really ln, I know I'm running out of room here, but that's ln of a to the negative 1. And using our properties, I can bring that down as a coefficient. So it's really negative ln of a. So we're gonna write this up here. So now I have negative ln of a plus ln of c over x minus 1 all over negative b. And then all they did is they just multiplied everything by negative 1, numerator and denominator. So that flips the signs of each of these. And I'm going to use this little space right here to put in our final answer in function notation. So f inverse of x, or f to the negative 1 of x, equals, and then we got positive ln of a minus ln of c over x minus 1 all over positive b. So that's your answer. Done. I hope you guys enjoyed this video, and if you did, please click that like button. If you want to see more from the Scalar Learning channel, make sure to click subscribe. Thank you guys so much for joining, and I'll see you in the next video. Take it easy.